Okay, so in section 12.2, we discuss factors that affect reaction rates. So we have to think about what must happen for a reaction to occur, and it sounds really obvious, but in order for a reaction to occur, the reactants must collide. And anything that it causes an increase in collision between reacting particles will increase the rate. And so a very obvious thing that we can do is we can increase the concentration of the reactants. So in this vessel here, I have one of each of my two reactants, and in this vessel over here, I've doubled the concentration of one of my reactants, and so as you would expect that you would get an increase in the reaction rate when I increase the concentration. So this has an interesting consequence because what it means is that as a reaction proceeds, the rate of the consumption of reactants will decrease. Initially, the rate of the concentration of reactants will be very high and the rate will be quick, and then as the reaction goes on, the concentration of the reactants decreases and hence the rate of the reaction slows down. So for any reaction, the rate is fastest at the time when the reactants are very first mixed. That is when time equals 0, and this is referred to as the initial rate. We're going to be talking a lot about the initial rate in subsequent sections. This all kind of, like I said, makes intuitive sense because in order for a reaction to occur, the reactants have to come into contact. So doubling the concentration or increasing the concentration in any way of our reactants will lead to a greater likelihood that the reactants are going to collide, and hence the rate will be faster. Now, when it comes to the reaction of solids, we have to recognize that solids interact through their surfaces. And so what this means is that finally dividing a solid, which will increase the surface area, will increase the rate of reaction. And you might have noticed this, if you take something like granulated sugar, it's going to dissolve a lot quicker than large lumps of sugar. This in fact can actually be an industrial hazard, and this is known as, in the example that is an industrial hazard is the example of a dust explosion, where you have a fine suspension of a flammable powder mixed in with air, and that can burn very quickly. And this often happens where we have sort of either grain silos is a classic example. You can see the side of this grain silo has been completely blown out, or in coal fires where you have a little bit of coal dust or a lot of coal dust suspended through air that can burn extremely quickly because we have a very, very large surface area in that case. So I'm going to show you a little video that illustrates this. So the video that I'm going to show you is the combustion of a spore called lycopodium powder.
This is a powder called lycopodium. Lycopodium is amazing because years ago it was used as a coating for vitamins. So here, watch this. So you see how it floats, Mark?
It does.
Now watch this. Take your finger and then dip your finger down inside and watch what happens. Ready? So dip your finger down inside and pull it back out again. Perfectly dry.
Oh, for heaven's
Isn't that
sakes, no
amazing?
water, just like a podium, but
Yep.
no water.
You got it. So it's hydrophobic, meaning water-fearing. Dip it down again and take a look at it. So it used to be the coating on vitamins.
I can feel the temperature of the water,
Isn't that
but I
amazing?
can't feel the
Yeah.
water itself.
Special effects artists, honestly, the burning sensation will go away in weeks, so it'll be fine.
And the rash.
Yeah.
The
Now,
burning sensation of the rash.
put
Go
your
on,
glasses
Dennis.
on. Put your glasses
Oh,
on. So now the other thing is that special effects artists use it, and you can imagine on the Ellen Studios the people that are around. By itself, watch this. If we put a little lycopodium here and we go to light it on fire, absolutely nothing
this
happens
can't
at all.
be-
Look,
Oh.
see? Nothing happens.
It's
kind of
inert.
like lighting a campfire. You have to stack the logs up so that oxygen can get around it. If you were to take this, however, and disperse it in the air, then we've got oxygen around each little particle. So here, light this on fire. So go ahead and it's okay. Just strike it. You know, push it forward. No, you have to.
Wait a minute.
No,
No,
push,
wait.
push that. Yes, now. Here,
got
I'll do
no
both.
idea.
All right,
Okay.
that's fine. All right, so you just stay and watch and enjoy. All right?
Okay.
So now just a little bit as it sits here. Isn't
Oh!
that just amazing? So this is what happens when you
That
have
was
oxygen
a coating
around.
for vitamins?
Well, but it's not used for this necessarily.
Okay, so you saw there the lycopodium powder. It's a very fine spore. When it's suspended in the air, it's highly flammable and it burns very, very quickly. The other thing, other than the concentration and the state of subdivision that will increase the rate of reaction, is increasing the temperature. So when you increase the temperature of a collection of particles, you increase the average speed of those particles. And we talked about that in Chapter 9 in Chemistry 161. if you increase the average speed of the particles, you increase the likelihood of them colliding. So if you were to stand up and start walking around your house randomly, so you could just kind of close your eyes, and you were to do that slowly, it would take you a while before you hit something. If you was to stand up, close your eyes, and start running, you would hit something very, very quickly. So by increasing the temperature, we increase the average speed of our particles, and we increase the likelihood of our particles colliding with each other, which increases the rate of reaction. And we probably know this from cooking. If you're trying to dissolve something in water, if you warm it up, it'll dissolve quicker. Now, when reactants collide, they have to do so with enough energy to break some bonds in the reactants and allow new bonds to form in the products. So when N2 reacts with O2 to form NO, we have to move electrons out of these NN bonds and move electrons out of these OO bonds, and then move some electrons in between the nitrogen and oxygen atoms. And all of that takes some energy. And so, the reactants have to come together with enough energy to allow all of that movement to occur. We have to have enough energy to break some bonds and form some new bonds. So the minimum amount of energy that the reactants must have in order to allow the reaction to occur is called the activation energy, and we give it the symbol EA. So here's an energy diagram for a reaction. This is fairly typical. We have energy on the y-axis, and we have progress of reaction, or it's sometimes labeled as reaction quotient. And what we have is reactants on the left and products on the right. And we know that this is an exothermic reaction because the reactants have lost energy when they form the products. And then here is the activation energy. It acts as an energy barrier. So the reactants have to have at least that energy in order to go on and form the products. So this helps us understand why increasing the temperature will increase the rate of the reaction. So at some lower temperature, T1, a relatively small number of molecules have enough energy to overcome the activation energy. But when we increase the temperature to T2, we have a much larger number of molecules that are able to overcome that activation barrier. So as temperature increases, the proportion of reactants with energy that is greater than the activation energy increases, and so the reaction rate goes quicker. So there is another thing that can speed up a reaction, and that's a catalyst. And what a catalyst is something that speeds up a reaction, but it's not actually consumed in the reaction. It's also present from the beginning. So it's a thing that we add to the reaction mixture rather than something that is produced along the way. And that'll become an important distinction later on. And so what catalysts do is they provide an alternative reaction pathway that has a lower activation energy. So here's my reactants, here's my products. The difference in energy between the reactants and the products is the enthalpy of the reaction. In this case, the reactants are losing energy, so it is exothermic. And so when the reaction is uncatalyzed, this is the activation energy way up there, but the catalyst provides an alternative pathway with a lot lower activation energy. So as a result, a greater proportion of the reactants have enough energy to overcome that activation barrier, and so the reaction goes quicker. So here it is, uncatalyzed. The activation energy is quite high. It's quite a long way along here. And then when it's catalyzed, we have a lower activation energy barrier, so we have a much greater fraction of the molecules that have enough energy to overcome that activation barrier.